Welcome to Recreational C Programming. Today we're going to do prime factorization because I thought that would be a fun problem. Also, it's a way to test against Wolfram Alpha because it will factor very large numbers. And it goes faster than my program does for some of them. I don't know why. Maybe they've got an IBM mainframe or something. I don't know, a laptop. So, 360 common number, 360 degrees in a circle. It factors down to 2 cubed plus 3 squared times 3 squared times 5. And I'm doing two things here with the code. One, and this is why I'm feeling kind of rushed right now, I'm using the Miller-Rabin test for primality, and I separated it out into a separate module because I'm using for the Goldbach conjecture from previous video. I haven't changed my Goldbach code yet, but I'm going to. But I have changed my prime factorization code, and I just finished minutes ago as I'm filming this. So, how do I handle tackling a prime number? Or, sorry, a composite number, because primes don't factor. I just spit it back out, actually. I literally do something called divide and conquer. Specifically, I have a find factor function, and it will take a big number and it will return the first factor it finds. And that's all it does. And it does 3 tests to do this. The first thing is, I'm going to use question marks, are we divisible by 2? Meaning even. If we are, I just return the 2. Are we prime? If so, I just return the number. After that, that's where I run into the heavy lifting. I've got a simple loop. Starts at 3. Is 3 it? No. How about 5? No. 7, no. 9, bop, 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 bop. Effectively, I'm trying all the odd numbers up to the square root of n. And either I'm going to get a number, or perhaps the Miller-Rabin test failed and I'm going to spit that number out. So that's what happens first. And yeah, it's broken out into a little function. So what do I do now that I've got a number? Like, I put in n, and now I have a factor. Well, I start dividing n by the factor in a loop, over and over and over and over until, while, I should say, n over factor blah equals 0. And I keep incrementing a number I call exponent each time through I do that. And then once I've completed doing this, by the way, I'm degrading n each time. I mean, I'm literally taking n divided by factor and assigning that back to n. So that basically reduces n to a smaller number. And then what I do is, if n is not 0, and I'll write that down, if n is not equal to 0, I repeat the process. I also do the same thing with the exponents recursively. So this program introduces recursion if you're not familiar with it. You know, basically you have a function and somewhere down here it calls itself with a different argument. And up here there has to be an escape clause, otherwise you'll go and blow your stack. So what else am I doing? I got my laptop here, don't worry. And really that is it. And by factoring out the Miller-Rabin code, because I'm using it for the test and I used it for the Goldbach conjecture, and I'm using it for a third program I'll talk about later. It has something to do with Collat's conjecture, which is something you're not supposed to look at because apparently it's a waste of time or something. An unprovable conjecture. Maybe, I don't know. Anyway, that's what I'm doing. So why don't we have a quick look at the code and call it a video. All right, if you've watched this far, I hope you give me a like, subscribe, and comment. Especially if you have any ideas of things you want to see. I mean, I'm up to ideas, or rather, I'm open to ideas. I am up to things, but best not anyone know about that. Okay, so this is the code for the prime factorization algorithm. And as you can see, I've moved external Miller-Rabin to its own module. That'll be in the GitHub repository. That makes it an annoying two-step process to get the code, because when you run the GitHub, get the repository code, it gets the prime factorization code, fine, and it'll even give you an external directory and a Miller-Rabin directory, but it will not put anything in the Miller-Rabin directory. Now, maybe that's something I did myself. Maybe it's a skill issue on my part. It's a possibility. Who knows? So what you would have to do then is go into the extern directory and pull down the Miller-Rabin code, a separate pull. So I'll have both links in the description. And I believe I've updated the README file to reflect that fact. So the find factor code that I was explaining, just pull that up to the top. Right here is a basic C-style classical testing for evenness. You can do mod 2, that would be more readable, but for whatever reason, out of habit, I like to do a binary test against, a bitwise test against the least significant bit being set to 1. So as we can see, I return 2 for an even number. And then I do the primality test. And if that passes, I return that number. And then the final step is, well, second to final. This return n should technically be unreachable code, but you never know. The Miller-Rabin test is probabilistic in nature. And if it misses 1, well, that drop down is in fact valid. So this is me counting through the even odd numbers. 3 is odd. Get that in your head. 3 is odd. And I'm not doing a square root function. I'm just multiplying the factor by itself. Mathematically, it's the same thing, but square root is an expensive function to do, so I do it this way. And as soon as I find something that is divisible evenly, I return that number. So that's what I explained on the whiteboard for find factor. I didn't write down the prime factorization code because it's a little longer, but it still fits on a screen. So clean code advocates don't need to scream at me. In fact, I'm not really sure how I would make this function, break it out into a bunch of different functions, but where there's a will, there's a way, right? So I'm looking for the first factor. And if it's my number, I just return. By the way, you'll notice this is a void function. It's basically just printing out its results directly. It's not storing them in some data structure for later. So if you wanted to save them out, well, I'll show you in a minute how to do that, but it's not difficult, really. Anyway, this is the loop I explained on the board where I do the divide and conquer. As you can see, this is an assignment statement. I'm giving n its value divided by the fac variable, my factor that I've found. So it's doing that while n is not equal, while n is not divisible by the factor. And after that, I print out the factor, and then I look at the exponent value. If it's greater than 1, that means I have a non-zero exponent. So I'm going to print out, even though this is the XOR operator in C, I'm going to print it out as an exponentiation because this isn't a typesetting program. And at this point, I test again to see if the exponent now is a prime number. If it's not a prime number, that means it can be factored down, in which case that's what I'll do. And that's my recursive call to prime factorization right here. And I use parentheses just for the, grouping. Although PEMDAS does apply, don't you worry. Anyway, if the exponent is not greater than 1, I just spit it out. Or rather, if the exponent was prime, I just spit it out. So it shouldn't have parentheses around them when it's not prime. But it'll build up parentheses for composite numbers. And if n has not yet been demolished, I know there are more factors, so I just print out a asterisk, you know, the multiplication symbol for C. And I just do this loop while n is greater than 1. I suppose I could do it while it's greater than 2, because I've already eaten the 2. Not a big deal. The main function is really just a test harness and also a way of gathering input. I did a few sample functions. It's not too bad. Let's time one. I have no idea how bad this one will be, but let's just remember, I suck at typing, folks. Let's see how long that one did take, roughly. So we can see it comes back pretty quickly. I can add a few more digits. Don't know what's going to happen, because sometimes you end up with a really big prime number in there that, well, big composite number in there, and it does something just like this. And this is the bit where Wolfram Alpha generally kills me, because I don't know how long this is going to take. I can edit it out if it doesn't take too long. Or I can get impatient and just kill it. And just try it with one less digit. Maybe this will be faster. Or maybe it won't. You never know. Because I've had numbers that take, minutes to come back, for example, and others that can go really, really, really fast. For example, it's not the size of the number, it's the size of the factors. As you can see. And there's a demonstration of the recursive calling, and here I am doing my finger again. There's a demonstration of the recursive calling going on. So only prime numbers come out. Anyway, this is definitely something, if you're interested in trying, you can try yourself. Like I said, Wolfram Alpha has a factor function that'll do the same thing. Generally faster, although for network latency, because really what's happening with the Wolfram Alpha program on the iPhone is it's sending off the question to the server, and then the server chews on it and then spits back a response. So there's some network latency going on there. So I can beat network latency to a point. If I stuck a 1 right after this, what would that do to it? Oh, well, you can see it took a lot longer, and the numbers came out completely different. And here you can see why it's taking longer. I had to count up through that guy, and I had to count up through this guy. And this big guy at the end, well, it passed the prime number test, so I didn't have to count up through that. My goodness, that would take forever. So on that note, I'm going to call this the end of the video. And yeah, I'm working on the Collatz conjecture. See what that does. But right now, yeah. Have a good day, week, month, year, century, life, whatever. And don't forget, like, subscribe, comment. Thank you very much.